Hello, in this video we are going to go over oxidation reactions of alcohols. So let's say we're starting with a secondary alcohol and we want to turn that into a ketone. That involves oxidation. Now, is oxidation a loss of electrons or a gain of electrons? A loss of electrons. And then we could always go back from the ketone to the alcohol, and that would involve reduction. Now, since reduction is the opposite process of oxidation, that means we would gain electrons. So looking at our alcohol, let's just do a quick question here. What is the oxidation number of that carbon attached to the alcohol? See if you can figure that out, and feel free to pause the video. So remember, when we're trying to determine an oxidation number, we first start with the number of valence electrons that the atom has. So carbon has 4 valence electrons, and then we subtract the number of electrons that the atom quote-unquote owns. So if we were to draw the Lewis structure, I'm just going to write CH3 for these groups off to the side. And then there is a hydrogen in the back. Carbon is more electronegative than hydrogen, so it's going to own both of those shared electrons. Carbon has the same electronegativity as our other carbons, so they would split those electrons equally. And then oxygen is more electronegative than carbon, so it would own both of those shared electrons. So it looks like carbon only has ownership over 4 total electrons. So we would subtract those 4 owned electrons from the valence electrons, and that gives us a value of 0. Now let's do the same thing for the carbon in our ketone. What is the oxidation number? And feel free to pause the video if you want to try to determine that by yourself. So again, carbon has 4 valence electrons, and then we're going to subtract the number of owned electrons. So if we draw the Lewis structure, we have a double bond with oxygen, and then our CH3 groups off to the side. So again, carbon is going to equally share the electrons with other carbons, and oxygen is more electronegative than carbon, so it will own all of those electrons in that double bond. So in the ketone, carbon only has ownership over 2 electrons. So that means it has an oxidation number of +2. All right, so if we're going from an alcohol to a ketone, our central carbon there is losing electrons, or its oxidation number is increasing. Okay. Now again, that's in reference to the central carbon that's bonded to the functional group. So let's go over the oxidation reactions of primary alcohols. Okay, so let's say we have a primary alcohol, and let's draw in our hydrogens on that carbon that's bonded to the alcohol. Okay, what if we performed an oxidation reaction? What would our product look like? So like we saw on the previous slide, the alcohol would turn into a carbonyl group. All right, and that actually involves the loss of a hydrogen. So after this oxidation step, we would only have one hydrogen left. And which functional group do we have here? An aldehyde. Now, what's also interesting is that if you have a strong enough oxidizer, the aldehyde can actually oxidize into a carboxylic acid. So we could go a step further here. So each time we perform an oxidation step, we're losing 2 electrons. So let's calculate the oxidation number of the carbon as we go from a primary alcohol to an aldehyde to a carboxylic acid. And feel free to pause the video to calculate the oxidation number. All right, so for the primary alcohol, again, we're starting with 4 valence electrons for that central carbon there. And that carbon has ownership over the shared electrons with hydrogen, so that's a total of 4. And then it also shares equally, I'll just kind of make some marks there. It shares equally the electrons with the methyl group, carbon. And then it has no ownership of the electrons that go to oxygen. So in total, it quote unquote owns 5 electrons. So carbon's oxidation number in the primary alcohol is -1. Now, an easy way to figure out the other oxidation states is we know we're losing 2 electrons each time. So that means the carbon is losing ownership of 2 electrons each time we go through an oxidation step. So for the aldehyde, that means that the carbon only owns 3 electrons compared to 5 in the primary alcohol. So its oxidation number in the aldehyde is +1. So that's a difference of 2. And then in the carboxylic acid, the carbon only has ownership over 1 electron. So its oxidation state is +3, and that's another difference of 2. Okay. So just getting some practice with oxidation numbers here. All right, now let's look at oxidation reactions of secondary alcohols. All right, so let's say we have another carbon group bonded to that central carbon. And remember, we still have 1 hydrogen here. Okay, so what product do we expect if we go through an oxidation reaction with a secondary alcohol? So again, that alcohol group turns into a carbonyl group, and we have our 2 methyl groups, and we lost that hydrogen. So this is a ketone. Okay, so we saw with primary alcohols we end up with an aldehyde, and because that aldehyde still had a hydrogen on it, that could be further oxidized to a carboxylic acid. But now with a secondary alcohol, we end up with a ketone, and that's it. We can't do any further oxidation steps. Now, we're still losing 2 electrons in that oxidation step. So let's figure out the oxidation number for the carbon atom in our secondary alcohol and in our ketone. And you can pause the video if you want to try that on your own first. All right, so again, that central carbon that I circled in red, that has 4 valence electrons, and in the secondary alcohol, it has ownership over both electrons going to hydrogen, and then it also has ownership over 1 electron to one of the carbons, and then another electron to the other carbon. So those are split equally. So that's a total of 4. So we have an oxidation number of 0. Now in the ketone, that carbon only has ownership over 2 electrons. So its oxidation number in the ketone is +2. And that makes sense because that gives us a difference of 2, and we lost 2 electrons. Now, what about tertiary alcohols? Let's look at oxidation reactions of tertiary alcohols. All right, so what product do we expect if we oxidize a tertiary alcohol? So you might be tempted to turn that alcohol into a carbonyl group, but what do you notice about this carbon in the middle? It has too many bonds to it, so we actually don't see any reaction for tertiary alcohols. Now, part of the reason for that is we don't have any hydrogens that we can lose. Whereas remember in primary alcohols, there were 2 hydrogens that we could lose. And then in our secondary alcohol, we had 1 hydrogen we could lose. But with a tertiary alcohol, we don't have any hydrogens to lose, so we can't perform oxidation on a tertiary alcohol. So that might be a trick question in the future, so just remember that detail. You cannot oxidize tertiary alcohols. All right, so we've been talking generally about oxidation reactions. What are the reagents that we use? How do we actually perform the oxidation reactions that we were talking about earlier? All right, so let's go over some oxidizing agents. Now, the main oxidizing agent that we use is called chromic acid. So chromium is in the middle, and it has a double bond to 2 different oxygens, and then it's also bonded to 2 alcohol groups. Now, there are 2 different ways that we can make chromic acid. You could start with something called chromium trioxide, which looks like this. And then you just treat that with sulfuric acid and acetone. Or you can start with something called sodium dichromate. So this has 2 sodium atoms on either side of the molecule, and those are just balancing the charge on the oxygens on either end. So the chemical formula for sodium dichromate is Na2Cr2O7. Oh, and I forgot the formula for chromium trioxide. That is just CrO3. Now, to turn sodium dichromate into chromic acid, we would use sulfuric acid again and water. Now, unfortunately, chromic acid is not the best reagent we could use. It is a strong oxidizer, so it is going to oxidize your sample, but it can cause cancer. And additionally, the byproducts of the reactions are not environmentally friendly. So later on, we'll talk about some other reagents we could use instead. But you should still know this reagent because you might see it on, for instance, a standardized test in the future. So just want to make sure you're aware of it. Okay, so let's go over an example where we use these oxidizing agents. So let's say we're starting with the following alcohol. And I'm going to draw in any hydrogens that are bonded to that central carbon there, bonded to the alcohol. And what is the name of this molecule? How would we name that? So the parent chain is the ring. How would we name that ring? Cyclohexane. And it has an alcohol group on it, so we're just going to replace the E on cyclohexane with OL. So it's cyclohexanol. And what type of alcohol do we have? Is it primary, secondary, or tertiary? Secondary, because the carbon that the alcohol is bonded to 2 other carbons. Okay, so if we oxidize a secondary alcohol, so let's say we're using sodium dichromate with sulfuric acid and water, what do we expect as our product? What do secondary alcohols turn into? Ketones. All right, so we would lose that hydrogen and we would turn our alcohol group into a ketone. And the name of our product is cyclohexanone. So ONE indicates that we have a ketone, but we'll learn how to name ketones later on, so don't worry too much about that. Okay, let's do another one. Okay, so what type of alcohol are we starting with for this reaction? Is it a primary, secondary, or tertiary alcohol? A primary alcohol because the carbon that the alcohol is bonded to is only bonded to one other carbon. All right. Now, after we oxidize that primary alcohol, what will we form? What do primary alcohols form after oxidation? An aldehyde. Oops. So we're going to lose one of the hydrogens that's bonded to that primary carbon, and we're going to change our alcohol group into a carbonyl group. And then we still have one hydrogen left. Now, because this chromic acid that we're using is so strongly oxidizing, unfortunately, we cannot isolate this aldehyde. Instead, we're going to go straight to a different product. And what would that product be? A carboxylic acid. All right. And let me just write aldehyde above our aldehyde intermediate, I guess you could say there. But again, we're not going to be able to isolate the aldehyde because this oxidizing agent is just too strong. So it's going to keep going to the carboxylic acid. Okay, so let's go over the mechanism for using chromic acid. So let's say we have a secondary alcohol. And we have our chromic acid as our oxidizer. Now, what ends up happening is the oxygen is going to bond to the chromic acid. So we kind of end up with this strange molecule here. All right, and, oh, sorry, one of those is a hydrogen. So let me just highlight the portion that ends up bonding to the chromic acid. And we would actually call this a chromate ester intermediate. And then we use water to deprotonate the oxygen. And then electrons are going to be left behind and form a double bond with oxygen. And the chromate is actually going to leave. So eventually we end up with our ketone. And then we also have an ion from our chromate ester. So don't worry too much about the mechanism. This one's a little more complex, so we'll just leave it there. But you kind of get the general idea of how the ketone is formed. Now, earlier I mentioned that we cannot isolate the aldehyde in our primary alcohol oxidation step because it just turns into a carboxylic acid pretty much right away. But what we could do is use something like a gentle oxidizer, so something that's not quite as oxidizing as chromic acid. And that will allow us to stop at the aldehyde if you really need to form one. Okay, so what we're going to use for this reaction is called pyridinium chlorochromate. And it's abbreviated PCC. PCC. So this is going to involve a mixture of pyridine and then chromate trioxide, or chromium trioxide, excuse me, and then hydrogen chloride. So that's going to make the following. And again, this will not be as oxidizing as chromic acid. However, this does have some negative effects. It is carcinogenic, so it can cause cancer. But let's look at an example of how we can use PCC. So let's say you have a primary alcohol. And again, remember previously we could not stop at the aldehyde. We went straight to the carboxylic acid. However, if you use PCC, and then let's say you just dissolve everything in dichloromethane, which is yet another carcinogenic molecule, you'll end up stopping at the aldehyde. So if you did use these reagents, you would want to be protected. You would want to wear gloves and just be really careful with all of the reagents. So are there any environmentally friendly reagents we could use for oxidation? Yes, there are. So let's go over some of those alternatives. So the first method for being environmentally friendly while performing oxidation is called Swern oxidation. And I think this was named after someone. But let's say you have a primary alcohol again. You can use something called oxalyl chloride. So COCl, and then there's two of those. And here I'll write the name up above, oxalyl chloride. I think I'm pronouncing that right. Some of these chemical names are a little tough to pronounce. DMSO, which is dimethyl sulfoxide, so we've seen that before. And we would also use a solvent such as dichloromethane, which again is not the best, but it works. And then we'd have to make sure this was all run at cold temperatures. But this would give us our aldehyde, and it's more environmentally friendly. Unfortunately, one of the byproducts of this reaction is dimethyl sulfide, which is a really smelly gas. So again, one of those sulfur compounds that we have to deal with. But if it's environmentally friendly, then maybe that's okay. Now there's another method called the Des-Martin pyridinane, I think it's called. I can't pronounce this either. But it's abbreviated DMP. And if you start with a primary alcohol again, you can just write DMP, and that will give you your aldehyde. However, there is a downside to this as well because nothing's perfect. This is explosive. So you have to be really careful when you're using these types of reagents. So again, you just can't win. There's always a downside to some of these chemical reactions. Okay, so let's go over an example. Let's practice using some of these reagents. So let's say that we have a diol. So we're going to kind of make this a little more challenging. And let's say we use excess PCC and everything was dissolved in dichloromethane, so that's just our solvent. What would our product be? And feel free to pause the video and try this on your own first, and then we can go over it together. And I'll give you a hint. It might help to draw some of the hydrogens in there. See how many oxidation steps you have. Okay, so I'm going to draw in my hydrogens on the carbons bonded to the alcohol groups. Okay. And let's see, what will we end up with here? So the first alcohol, what will that turn into? Will it turn into an aldehyde or a ketone or a carboxylic acid? So we just said that PCC will allow us to stop at the aldehyde if we have a primary alcohol, and the alcohol I underlined is a primary alcohol. So we'll stop at the aldehyde for that one. Okay. What about our other alcohol? What will that turn into? A ketone. So that one is a secondary alcohol. So if we oxidize it, that will turn into a ketone. Oh gosh, I drew this molecule so poorly. Let me redraw it. It's a little wobbly. Let's see. So I'm trying to make it look like this. And then the hydrogen is up there. So even though we said that PCC will allow us to stop at an aldehyde for a primary alcohol, that doesn't mean that it can't oxidize anything else. It can oxidize a secondary alcohol into a ketone as well. So let's just make a note. PCC can also oxidize secondary alcohols, because that might get a little confusing sometimes. All right, so now we have an aldehyde and a ketone in our final product. Okay, so let's just summarize our chapter here. And actually, we're going to summarize pretty much everything we've learned up to this point. And this chart is super helpful. It's a really nice reaction map that just really puts everything together. So you'll notice in the upper left-hand corner, we start with our alkynes, and then we can see how to reduce that into an alkene. And vice versa, we can also go back to an alkyne. And then from alkenes, we could go to our alkanes, or we could go down to alcohols, alkyl halides, and notice that there are reagents listed, and there's also options listed. If you start with an alkyne, you could also go down to a ketone or an aldehyde. And then we can go from a ketone or an aldehyde to an alcohol, or in reverse. And then you can see we could go from an alcohol to an alkene, or to an alkyl halide, etc. So there's a lot of different reagents listed here, a lot of different ways we can go back and forth between functional groups. And as we go forward this quarter, we're going to learn even more reactions that we can then add on to this chart. So I highly recommend referencing this chart when you're working on your problems of the day, or even on your homework on sapling. This can be really useful as a guide. All right, so that's the end of chapter 12, our alcohol chapter. In the next chapter, we're going to learn about ethers and epoxides. So I will see you then.